signs that we have interactions. Here, we don't need that on. Include change of speed, right? So we'll now write this as the magnitude of the velocity. Change of direction. Well, we can now write that as the unit vector in the direction of the velocity. Or we can actually put this together and say just change of velocity, a vector. There are other changes that indicate interactions. Not velocity isn't the only thing. So, for example, if we take an electron, and you know what an electron is, very small negatively charged particle. Negative electrons surround the positive nucleus in atoms. Mass is about 9 times 10 to the minus 31 kilograms. Well, suppose you have an electron going this way, and over here you have a positron. What's positron? Well, positron is also a very tiny particle with the same mass as the mass of electron, about 9 times 10 to the minus 31 kilograms, but it's got a positive charge. So this has a charge of minus 1.6 times 10 to the minus 19th coulombs, and this has a charge of plus 1.6 times 10 to the minus 19th coulombs. It's a particle of antimatter, so it's a positron. They're fairly easy to make in reactions and accelerators, so we actually get beams of positrons fairly easily in accelerators like Fermilab or the Large Hadron Collider at CERN. Well, if these two things come together and they actually touch, they annihilate each other, because electrons ordinary matter, positrons antimatter, they annihilate. And so what we actually end up with is two photons, two little particles of light. They're called gamma rays. So there's two gamma rays. So the electron is now gone, and the positron is now gone, and what we've got are two photons, two high-energy light particles traveling through space. We call this a change of identity, because the electron has lost its identity as an electron. It's had an identity crisis. It's no longer an electron. It's gone, and now we have gamma rays. So we have what we call change of identity. That's a sure sign that there was an interaction. There's some other signs. If we take the spring that we saw in the program here and we stretch it, it changes shape or configuration. Well, it's not going to do that by itself. It does it because we stretched it or because we hung a weight from it. So change of shape or configuration also is an indicator of interaction. For macroscopic objects that are made of lots and lots of different atoms, there's another indicator of interaction. So suppose I rub this book on the table. The book and the table are a little warmer. They get hot. Rub your hands together, your hands get hot. Change of temperature is also an indication of interaction. Now, sometimes we have to do a little reasoning, a little deductive reasoning to deduce interactions. And here's a very simple example. Here's an object that is currently at rest, so its velocity is 0, speed is 0, direction is undefined. If I let go, it falls down. Why did it fall? Yeah, so what's the object in the surroundings that it was interacting with? The Earth. Good. Okay. We know that this marker is interacting with the Earth. You're interacting with the Earth. Your chair is interacting with the Earth. We're all interacting with the Earth. However, the velocity of this marker is currently not changing. Therefore, we deduce, like Sherlock Holmes, that there's some other interaction that's canceling out the interaction with the Earth. So we deduce when we think there should be a change and there isn't a change, we deduce that there's some interaction we haven't taken into account, and in this case, clearly, it's the force of my hand exerting an upward force on the marker, so it's not falling down. So the absence of change when you know there's an interaction should suggest to you that you better look for another interaction. Play detective. Okay, so that's the basic idea behind what we're going to be doing, and we're going to try to make this precise by first describing velocity precisely and then extending that concept to a more fundamental concept, which is the concept of momentum. Just to practice, though, here is our first clicker question, which is a question about interactions. Okay, I'm going to start polling. Here's the question. Some moving objects left the traces shown there. So we have, and these traces, these objects left dots at equal time intervals. So the object moving here left a dot every second. This object left a dot every second. That object left a dot every second. So each object moved along and left a dot in its trail every second. Which objects did not, can you deduce by looking at these trails, did not interact with something in the surroundings while they were moving? Okay. Now, if you don't have a clicker, you're going to need one by next week because the quiz on Wednesday counts, and you have to have a clicker for the quiz. If you don't have a clicker, what you need to do is write down on a piece of paper what your answer is so that you can't kid yourself when we talk about what the answers are. So commit yourself by writing down on a piece of paper 1 through 7. Okay? Okay, so you think this is really easy and not worth talking to your neighbor about. All right, well, that's enough time in any event, so we will stop polling. And the most popular answer is 1, but there's also 5 is semi-popular, and then 6 and 7. So let's see what those answers were. Okay, A is 1, and we conclude that you probably concluded that it didn't interact with anything because the time in between the dots, the space in between the dots is constant, meaning that it was going at constant speed, and the direction didn't change, so that's correct. B looks like it actually sped up because the dots get farther apart. But what about D? I mean, some people did actually say D, or some people said A and D. Well, that just means it didn't get all the way around. Okay, it just didn't have, it was going at some speed where it didn't. Its direction's changing, isn't it? So we really got to think about the speed. It looks like it was going at constant speed, but the direction was changing. So up here it was going here. Down there it was. So even though the speed was constant, the direction was not, and that meant it had to interact with something. It wouldn't have gone in a circle all by itself with no cause.